Thank you. Thank you for inviting me to speak. So please feel very free to ask questions at any point during this talk. Parts of it are written assuming some background material. If you have any, I can try to fill it in, or if you have any other kind of question. I want to begin. This whole talk is going to be about perverse sheaves. So I want to begin by giving either a quick review or a very, very brief introduction to the notion of a perverse sheaf. And you can think of them as in a couple different ways. But one way I like to think about them is as solutions to a problem with the ordinary notion of sheaves, which is that different sheaves have their most interesting cohomology in very different degrees. If we begin, if we have a variety and maybe some x and some smooth subvariety y, a nice sheaf is obtained by taking any kind of locally constant sheaf on y and extending it to x by push forward. And if you do that, the cohomology of your sheaf will equal the cohomology of y with coefficients in a locally constant sheaf, which by cohomological dimension results we know is concentrated between degree 0 and degree twice the dimension of y. And there's a Poincare duality between degree I and 2d minus I. And then the most interesting degree is always the degree which is stable under Poincare duality, which is d. So it depends on the dimension of y. And that's sort of inconvenient for the category of sheaves. And so what perverse sheaves do is they fix this. So the local constant sheaf on y only becomes a perverse sheaf when you shift this degree down by d. And so it'll have cohomology in degree between minus d and d. And the duality is between I and minus I, so it centers around 0. The most interesting cohomology is degree 0, regardless of your choice of sheaf. And so what's remarkable is when you do this, when you define the correct category of complexes of sheaves satisfying, the correct generalization of this condition to allow singularities, not only does it have this nice property of cohomology, it also has all the nice properties the original category of sheaves had, for example, forming an abelian category and gluing condition, and it has even further nice properties besides. So formally what you have to say is that the cohomology in degree minus d of your complex of sheaves had better have support in dimension less or equal to d for all d, and the same should be true of the dual complex.
It's k, so not x, h minus d.
Oh yeah, of k, yes. Very true. And so in very concrete terms, what that means, you have a complex of sheaves with no cohomology in positive degrees and maybe finally many points in degree 0, and as the degrees get lower and lower, the support of the cohomology gets larger and larger. And that's a general statement for all perverse sheaves, and we're going to try to get more precise understanding of the different cohomology objects for a specific perverse sheaf, in particular ideally for perverse sheaves that we construct as part of some broader geometric problem. So the other concept that I want to review or briefly introduce is the characteristic cycle, which related to what appeared in previous talks. And so this is always going to be, we're going to work with a perverse sheaf on a smooth variety dimension n, and we're going to look for
the variety of dimension n over what?
Over a perfect field, let's say. And we're going to look at a effective cycle of dimension n in the cotangent bundle of x. So it's going to be a combination of n-dimensional irreducible subvarieties of the cotangent bundle that have with non-negative integer coefficients. And so this was defined a while ago for varieties over a field of characteristic 0 using kind of complex number techniques. And it was only recently defined over a field of characteristics P by Saito. And the irreducible subvarieties that appear in the characteristic cycle are not arbitrary. They are conical, meaning they're invariant under the action of GM by scaling the cotangent bundle. And in characteristic 0, you can say something even further. They're Lagrangian. This natural symplectic form in the cotangent bundle vanishes on these subvarieties, but that is not necessarily true in characteristic P. And the way that you define the characteristic cycle in characteristic P is by using the Milnor Formula, which is a property satisfied by the characteristic cycle, which I'll discuss on the next slide, and it generalizes this very classical formula of Milnor for the dimension of the space of vanishing cycles of an isolated singularity. And so the setting of the formula is you have a map from your variety X to a curve C, or maybe from an open subset of your variety to a curve. We're going to look at the derivative of this map. And the derivative of this map, we can think of it as a differential form on X, so a section of the cotangent bundle. And we can do that as soon as we fix a global differential form on C, which, for example, if C is the affine line, this is very easy to do. We're going to look at the vanishing cycles complex of the perverse sheaf K along the map F. And the first property that the characteristic cycle should satisfy is that the vanishing cycles should only exist on the intersection of df with this cycle. And when that intersection is isolated, so that means that the vanishing cycle sheaf will have an isolated point of its support, then the intersection number carries a meaning. The intersection number of the section df with this characteristic cycle will equal to the dimension of the space of vanishing cycles plus the Sawin conductor, which measures wild ramification. So in characteristic 0, there's the Sawin conductor vanishes, and so the simpler formula is that the dimension of vanishing cycles is equal to this intersection number. And if your perverse sheaf is
we have a question. We have a question.
Yes. So I think usually there is some minus ones in the formulas. For example, here if K is perverse, then R F is a shift of perverse. So
yeah,
you get a minus one. You cannot avoid some.
Well, I mean, I can by the following thing, which is if it's supported at an isolated point, it's supported in degree -1. So if I just don't take the Euler characteristic and just take the raw dimension, then I don't get the -1.
Okay.
And I thought it was simpler because I would be introducing a -1 by the Euler characteristic. Like I get why you do it for the general complex of sheaves, but if we just have a perverse sheaf, it seems simpler to just not introduce the -1.
Okay, and in characteristic,
I know about the -1. I haven't forgotten it.
Okay, and in characteristic 0, so the coefficients are like a field, but it could be either like Q, C, or also Z mod L in characteristic 0. So you can use D modules when you are working with characteristic 0 coefficients, but was mod A. So in characteristic 0 it is the Kashiwara-Shapira theory of singular support. So what is the reference in characteristic 0? You said it is known in characteristic 0.
I don't know the reference off the top of my head. I just, I mean, I think that the proof in characteristic P works in characteristic 0 also. So, or is there? I think it does, right? So one could give that as a reference, although that would be pretty silly. But I think the reference is contained in Saido's paper. But yeah, so this is a good point. So the characteristic cycle in characteristic P, we define it as the unique cycle satisfying this Milnor formula. In characteristic 0, in the setting of complex coefficients, you can use D modules, and there's a very natural definition using D modules, which I, however, won't get into because it's not useful for what I'm going to discuss in the rest of the talk. But there's like a good motivation for the characteristic cycle in that setting. And in that case, the Milnor formula says dimension of vanishing cycles equals intersection number. For the constant sheaf, the character cycle is just the zero section. And so we're intersecting this differential form with the zero section. And so from that definition, it's not so hard to see why it's equivalent to the statement people usually give of Milnor's work, which is in terms of the quotient ring by all the derivatives of the map F. If you do mod by the directional derivatives, the quotient ring has dimension equal to the intersection. And so for the purpose of this talk, the actual only thing that's important about the Sawin conductor is that it'll be non-negative. So the only part of the Milnor formula I'll use is that the intersection number gives an upper bound for the dimension of the vanishing cycles. So the characteristic cycle, by definition, it tells you about the vanishing cycles of your sheaf, but it also tells you about a bunch of other stuff. So I guess one property I didn't write down is the characteristic cycle. If you intersect it with a zero section and have a global intersection number, that will tell you about the Euler characteristic of your variety. But there is another property the characteristic cycle tells you about your sheaf, is it actually gives information on the dimensions of the stalks of the various cohomology sheaves. And this was done in characteristic zero by David Massey. And so to describe what he's doing, let me first recall that, or I don't know, recall, mention that given perverse sheaf, its cohomology can be non-vanishing only in degrees from 0 to minus n. And so when we're trying to understand what is the stalk at a particular point, we need to figure out is that how big is the stalk? What's the dimension of the stalk in dimension from 0 to minus n? And what Massey did was give an upper bound for that dimension in each degree in terms of some intersection-theoretic invariants of the characteristic cycle, which are called the polar multiplicities of the characteristic cycle. And this is some kind of generalization of the usual notion of multiplicity in algebraic geometry. You can take the multiplicity of a variety at a point or a multiplicity of a cycle at a point, and you can do it by intersecting it with a generic smooth variety of complementary dimension at that point and estimating the local intersection. And so the next couple slides, I'll explain what these polar multiplicities are. So one can define them for any conical cycle in the cotangent bundle of dimension n. So I'll write C to refer to a general cycle, which is not necessarily the cotangent, the characteristic cycle of anything. And of these, two of them are the easiest to find, the very first one and the last one. And so they're defined just using the notion of, just using kind of the definition of an algebraic cycle as a non-negative integer combination of irreducible subvarieties, not even using any intersection theory. The zeroth polar multiplicity counts how many times the cotangent space at the point y, or the fiber over y, appears in this sum. And the nth polar multiplicity counts the number of times the zero section appears in this sum. And I want to point out that these two have very contrasting behavior. So the zeroth polar multiplicity can only be non-zero at finitely many points, because you can only have finitely many different fibers appearing in the sum, which is good because we're going to want to use it to give an upper bound for the cohomology in degree 0, which we know is only supported at finitely many points. And the nth polar multiplicity has the opposite behavior. It takes the same value at any point. If it's non-zero at 1, it's non-zero at all of them. And that's also good because we're going to try to use that to bound the cohomology in degree minus n, which can be supported at many different points, at all the points. And so as you get higher and higher, the polar multiplicities become they measure your cycle more and more spread out over the variety. They're interested in components of the cycle that are more spread out as I grows. And then they correspond to the cohomology groups being more evenly spread out over the variety. And before I give the general definition, I'll mention the third easiest to define polar multiplicity, which is the n-1st polar multiplicity. And so the way you define that is you projectivize the cotangent bundle. You remove the zero section and mod out by scaling. And then because C is conical, which I haven't used yet, we can projectivize C as well. We can remove a zero section from C if it appears, and then mod out by scaling, and we get a cycle of dimension n-1 on the projectivized cotangent bundle. And then you can push forward that cycle using the natural map from the projectivized cotangent bundle to X. And we'll get a cycle of dimension n-1 on X, which is a hypersurface on X. And so the n-1st polar multiplicity at Y is defined to be the multiplicity of that hypersurface at Y. So the order of vanishing of a polynomial defining that hypersurface, equivalently the intersection number with a generic smooth curve at that point. So it's going to be supported on a hypersurface. And the general case is going to be constructed by a similar means. Or we're going to again start by taking the projectivized cotangent bundle of X and projectivizing C inside that. So it'll be a cycle of dimension n-1. But then we're going to introduce something a little bit more. We're going to introduce a generic sub-vector bundle of the cotangent bundle of rank I+1. Defined at least in a neighborhood of the point Y. It doesn't have to be globally defined. And we'll projectivize that sub-vector bundle. So we now get a projective space bundle of dimension I. And so we're going to intersect the projectivized cycle with the projectivized cotangent bundle and push forward down to X. That produces a cycle of dimension I, and we'll take the multiplicity, the usual multiplicity of that cycle at Y, and that defines the I polar multiplicity of our original cycle. And if we do that for V sufficiently generic, it'll be independent of the choice of V, and that's the one we want to take. And so what Massey proved is that this ith polar multiplicity is a bound for the stalk in degree minus I at Y. And he proved this in characteristic 0. So the main theorem is going to be the same statement Massey proved in characteristic P for a perverse sheaf on a smooth variety over a perfect field of characteristic P for any point in X. The dimension of the cohomology in degree minus I at the point Y is at most the ith polar multiplicity of the characteristic cycle of K at Y. Does anyone have questions about this statement?
So this is for coefficients in Z torsion coefficient or QL coefficients, or and the work of Massey was both, or what was exactly the?
I think Massey worked with Q coefficients. Sorry, I think I wrote it down for QL coefficients, but it probably works for both. I just kind of like QL coefficients. That's what I like. Yeah, there's no weights or anything that is intrinsically QL used in the proof. So I think it should be fine for both. So what I'd like to do next is talk about the motivation for this theorem in terms of what are some results that you can prove with it. And when I'm done with that, I'll say something about the proof. And for me, the main motivation for this theorem comes from the theory of trace functions. So a trace function is obtained in this context from a perverse sheaf on a variety over a finite field. And it's a function on the finite field valued points of that variety. And you define it using the fact that Frobenius acts on the stalk of the perverse sheaf at any finite field valued point. So you take the trace of Frobenius on the stalk of the minus ith cohomology at your point y, you sum it over I with an alternating sum. So it's times minus 1 to the I. So this definition might at first appear somewhat arbitrary, or at least a little bit arbitrary if you've seen, I don't know, the leftist fixed point formula maybe a little bit less arbitrary. But it turns out that a remarkably large amount of functions of interest in mathematics are trace functions of perverse sheaves. So this occurs a lot in number theory, and it also, in representation theory, and it also occurs a ton in number theory associated to polynomials of finite fields. So a lot of times we can take functions of interest in number theory that depend on, say, a number or some other kind of arithmetic object. And we can consider analogous functions where we replace all notions of integers with polynomials over a finite field in one variable. And then when we do that, an arithmetic object like a number becomes a geometric object like a polynomial that's parameterized by some high dimensional moduli space over a finite field. So polynomials are parameterized by like affine spaces. Residue classes are going to be parameterized by some kind of torus, some kind of algebraic group, or invertible residue classes at least. The analog of ideal classes in number fields becomes like line bundles in this function field setting and are parameterized by the Jacobian. And the analog of the Mausler curve is often the moduli space of G bundles. And so it's a remarkable fact that a lot of the functions of most interest in number theory are not just arbitrary functions on these points of varieties or finite fields when you consider their analogs in this geometric setting. They are in fact trace functions of perverse sheaves. And that means you could hope to use theorems about perverse sheaves to study these functions. So in particular, you can often prove a purity property of the perverse sheaf, which would imply that the eigenvalues of Frobenius on the minus ith cohomology group are bounded by q to the minus I over 2. And so as soon as you have a bound for the eigenvalues of Frobenius on a vector space, and you have a bound for the dimension of the vector space from Massey's formula, that gives you a bound for the trace. And so anytime you have a pure perverse sheaf, this formula gives you a bound for the trace function in terms of the character cycle. And that turns out to be a powerful tool. And I'll talk about 3 different applications of that idea. So I'm going to go over these, briefly. So hopefully, I'm not expecting all of the applications to make a lot of sense to everyone, but hopefully at least one of them will make sense to a lot of people. Feel free to ask me questions if something doesn't make sense to you. So one of the most famous examples of perverse sheaves with interesting trace function is Hecke eigensheaves, which are the foundations of geometric Langlands theory. And these are sheaves that are on the moduli space of G bundles on a smooth projective curve C. And the interesting thing about the moduli space of G bundles is its set of FQ points for a finite field FQ has an arithmetic interpretation. So there's a parameterization due to they that tells you that this is equal to the adelic points of the group modulo the rational points of the group over this field F, the field of functions of the curve, and then modulo the standard maximal compact subgroup. And so this is exactly the kind of double coset construction that you can use to make modular curves in number theory and chimera varieties and other spaces which automorphic forms live on. And so the trace function of a Hacke eigensheaf gives you an automorphic form, and justifying the name, it's in fact a Hacke eigenform. And so what happens when you plug the Hacke eigensheaf into this Massey type formula in characteristic P? It gives you a bound for the values of the automorphic form, at least assuming that you can calculate the input to the formula. You can calculate the characteristic cycle, you can control the polar multiplicities, and get an actual number out of it. And so this question about how large values does an automorphic form take is a kind of more like naive question than a lot of the very sophisticated questions about automorphic forms that are asked, that are studied in like Langland's theory. But it is still a reasonable question. It's something people study in analytic number theory. What is the largest value obtained by a given automorphic form, also known as the soup norm? So they call it the soup norm problem. And that's kind of a very hard problem in general. There are a lot of subtleties. Even applying geometric methods, there's many difficulties, but I was able to make progress on it using this formula in kind of the simplest case, in the case where the group is GL2 and the curve is P1, and we put some square-free level structure. So we allow our bundles, we give them parabolic structure at some finitely many points. And so a second application I want to give is to a kind of even more classical problem in analytic number theory, which is about the number of primes in an arithmetic progression. You would like to have good upper and lower bounds for how many primes there are up to a given distance in a given arithmetic progression. And so there's an analog of this for polynomials over finite fields, where you count, because the analog of primes are irreducible polynomials, you count the number of irreducible polynomials to the degree n, which are congruent to a fixed residue class A, modulo a fixed polynomial G. So I stated this is about estimating a number, about counting something, but to apply the machinery of perverse sheaves, we want to turn it into a question of a function. And so we view this count as a function on the set of invertible residue classes A modulo the polynomial G, because primes are always, or almost always, invertible modulo G. And you can think of that set as the finite field valued points of a certain algebraic variety, a torus or a generalized Jacobian. This number of primes turns out to be not literally the trace function of a perverse sheaf, but a constant plus a linear combination of trace functions of perverse sheaves. And the constant is very easy to understand. It gives kind of the main term of the problem. So the main difficulty is to control the trace function of the perverse sheaves. And that's something you can do using a combination of the Massey formula together with some other geometric tools. At least in the case where G is a square-free polynomial, I figured out how to do this. And it actually works much more generally. Rather than counting primes, we can count products of two primes or products of primes of very particular degrees. We can count many different special types of polynomials. So the third application I want to talk about has to do with the conjecture of Michel-Venkatesh, which has to do with CM points in a product of two modular curves, say x of n times x of n. And if you look at one CM point, and you look at its Galois orbit, the conjecture is this should be evenly distributed in the product of modular curves as the number of points in the orbit goes to infinity, ignoring some subtleties. So that as the number of points goes larger and larger, the proportion of them in any region should match the volume of that region according to the natural uniform measure on the modular curve. And so this conjecture is closely related to the under-Earth conjecture. It's kind of a strengthening of the under-Earth conjecture for the product of two modular curves, because the under-Earth conjecture says CM points can't be concentrated in the subvariety, and so it's stronger to know they're evenly distributed over the whole space. And so the under-Earth conjecture was recently resolved, but we still don't know in complete generality this result of Michel-Venkatesh, although there's been progress on that also, particularly by Kayutin. And so this problem also has an analog in function fields for polynomials or finite fields. It's a little subtler to figure out what the correct analogs of the modular curve and CM points are in this setting. But you can, and kind of in the simplest case, the analog of the modular curve is going to be, again, the moduli space Bunge, specifically Bunge-L2. So the moduli space of rank 2 vector bundles on, for simplicity, P1. And Galois orbits of CM points can be parameterized by the class group. So we're looking at the most interesting cases when we have CM points which have the same CM field on both sides, on both copies of the modular curve. And so we get, and those are parameterized by elements of the class group of that CM field. And so the functional analog of the class group is going to be the FQ points of the Jacobian variety. So the relevant function that we're going to consider is we can pick our favorite points on Bunge-L2, across Bunge-L2, and say how, for each point of the Jacobian, how many of the CM points in that Galois orbit map to a given point in Bunge-L2 across Bunge-L2. And equidistribution is equivalent to having some sufficiently good upper and lower bounds for that particular function, which I want to think of as a function on the FQ points of the Jacobian. And this function you can also express as the trace function of a perverse sheaf up to a constant. And you can apply the Massey formula to get a bound, and the bound is strong enough to prove an equidistribution statement. And this idea, this strategy was developed by Schende and Zimmerman on this problem. And they did the entire argument, but they ran into trouble. They didn't have this characteristic B Massey formula. So they only knew the Massey formula characteristic 0. So what they did is they followed the argument up into the place where they needed to use the Massey formula, and they went to characteristic 0, and they said it's true in characteristic 0, so it's reasonable to believe it's true in characteristic B. So then my work kind of filled the gap in their argument. So in the remaining time, I'll try to say something about the idea about the proof. Get some water again. So the key tool used in this proof is going to be the vanishing cycles long exact sequence for a map F from our variety X. So we have a perverse sheaf. We want to bound its stalk cohomology in a given degree. And we're going to write out for any F the vanishing cycles long exact sequence where the stalk cohomology maps to the stalk of the nearby cycles, maps to the stalk of the vanishing cycles, and loops around. And if we choose F sufficiently generically, we'll have a lot of control on the stalks of the nearby cycles and vanishing cycles. So we can choose F so that the point Y is at most an isolated intersection point of DF in the characteristic cycle, which is going to tell us the vanishing cycle is supported as a single point, and that's going to tell us by some kind of perversity that it's supported in degree -1. So this vanishing cycle sheaf is going to be non-zero only in degree -1. And the nearby cycles is also going to have a perversity property, and that will tell us it vanishes for I less than -n and greater than -1. And if you plug those vanishing into the long exact sequence, you see that it simplifies tremendously. So in any degree less than 0, the cohomology of the stalk is going to be bounded by the cohomology of the nearby cycles. And in degree 0, the cohomology of the stalk is going to be bounded by the degree of the vanishing cycles. So to prove that nearby cycles is bounded by the ith. To prove that the stalk in degree -I is bounded by the ith polar multiplicity, we can divide up into two parts. First, the stalk in degree -I of the nearby cycles is bounded by the ith polar multiplicity. And second, the stalk in degree -1 of the vanishing cycles is bounded by the 0th polar multiplicity. And we're going to handle those two basically separately. So the vanishing cycle step is unsurprisingly where we're going to use the Milnor formula. So what the Milnor formula tells us is that the dimension of the stalk of the vanishing cycle with the point Y is at most the intersection number of the characteristic cycle with the graph of DF at the point Y. And then we're going to choose F generically. So we can use the fact that DF is going to be a generic point of the fiber over Y. And being a generic point, it's not going to intersect any subvariety of the fiber except for the whole thing, right? Any finite list of subvarieties except for the whole thing. So any irreducible component of the characteristic cycle, which is not equal to the fiber, its intersection with the fiber will have dimension less than n, and so it will not intersect DF. So the only irreducible component of the characteristic cycle that contributes to the intersection is going to be the fiber, and the number of times it contributes to the intersection is equal to the number of times it appears, which by definition is a 0th polar multiplicity. So it works almost directly from the Milnor formula. The other step is going to be a little bit more complicated. So here we really want to take advantage of the fact that the nearby cycles is a perverse sheaf up to a shift by 1. So I wrote that in a somewhat strange way. And we're going to use an argument by induction because the nearby cycles is a perverse sheaf on the fiber of F containing Y. So it's on some hypersurface in the variety X, which is 1 dimension lower. And so we're going to make an induction hypothesis that it's true in dimension n-1. And then we need to bound the cohomology of the nearby cycle sheaf, and we'll do that by bounding the polar multiplicity of the nearby cycle sheaf. In fact, what we'll show is that I minus first polar multiplicity of the characteristic cycle of the nearby cycles is going to equal the ith polar multiplicity of the characteristic cycle of the perverse sheaf, again, as long as F is sufficiently generic. And we'll do that in 2 steps. We're going to first give a formula relating the 2 characteristic cycles, and then we're going to see what that implies about the polar multiplicities. So as a warm-up to talking about the characteristic cycle of the nearby cycles, I want to talk about the characteristic cycle of a pullback. So what we're going to do is we're going to be pulling back to the fiber of F containing Y, which I'll call H, and I'll let I be the inclusion of H into X. And the nearby cycles is going to be related to the pullback by a vanishing cycles long exact sequence. So it's helpful to understand the pullback first. And luckily, This is something that has already been worked out. So Saito has a formula for the characteristic cycle of the pullback. And so the simplest thing you might hope for is that the characteristic cycle of the pullback is the pullback of the characteristic cycle. But that unfortunately does not make sense because you can't write down a natural map from the cotangent bundle of H to the cotangent bundle of X. The map you can write down is the derivative of the inclusion I. If you look at what that does on the cotangent bundle, you can see it maps the cotangent bundle of X fiber producted with H over X to the cotangent bundle at H. So you have a point in X which actually comes from H, and you have a cotangent vector. You can pull it back under the derivative, and you get a cotangent vector of H. And the formula for the characteristic cycle of this pullback is you take the push forward along di of the pullback from T star X to its fiber product over X with H of the characteristic cycle. And this is called I shriek of the characteristic cycle. And this is true as long as this map I is sufficiently generic. So you have to check it satisfies some genericity hypotheses. So here is my claimed formula for the characteristic cycle of the nearby cycles. What you first do is if the fiber over Y, if the cotangent space appears in the characteristic cycle, you just get rid of it. You subtract off that term. And then you apply this operation I shriek. You pull it and you push. And to show this formula correctly gives the characteristic cycle near the point Y, it's convenient to first show it at every point other than Y. So in particular, you can show it where df does not intersect the characteristic cycle, since in that case there's no vanishing cycles, which means the nearby cycles are equal to the pullback. And then Saito's formula gives you the characteristic cycle of the pullback. So because we know this at everywhere except for the intersection point, then our best hope to prove this is if there's only one intersection point. So that's what I want to assume. The only possible intersection point is Y, so this formula is correct except possibly at Y. So the only possible error is like a cotangent fiber over Y. And so we can eliminate this using the Euler characteristic formula, using the fact that the global intersection of the characteristic cycle with the zero section is equal to the Euler characteristic. If my formula were not correct, then the Euler characteristic would not equal the Euler characteristic predicted by the formula, because the fiber over Y, if you put a different multiple of that, it would contribute to the Euler characteristic. So you just have to check that the Euler characteristic does agree with what's predicted by the formula. And so you can do that because the Euler characteristic of the nearby cycles complex is equal to the Euler characteristic of the generic fiber with coefficients in K by the fundamental property of nearby cycles. And then you can then compute the Euler characteristic of the generic fiber using the characteristic cycle, and you can compare the two. So that gives us a formula for the characteristic cycle, which is proved to be valid under a kind of global assumption, under the assumption that df intersects characteristic cycle only once in the fiber of F containing Y. So what we need to do to run the argument, we need to construct such a map. We need to construct a map from X to the projective line such that the derivative intersects the characteristic cycle only at Y, and we need some other genericity conditions to make the pullback step work. And in the characteristic zero argument, you would use like a generic analytic function to do this. You would like work locally, and you would choose a general complex analytic map. We're working in characteristic P, so we only have access to algebraic maps. And so it turns out it suffices to choose a pencil of quadrics for the map. So basically a map of degree 2. So we embed X in projective space, and we'll choose a generic pencil of quadrics. So that gives a map not out of X, but some blow up of X. And so we had to deal with that. So we first calculate the characteristic cycle of the pullback to some blow up using Saito's formula, and then we run this nearby cycles, vanishing cycles argument. So there's a bunch of genericity conditions we have to check. we have to check genericity conditions of the blow up, and then genericity conditions for the fiber, and then we have to check that DF only intersects the character cycle once. And I'm going to check them in the same way, which is a very concrete way by dimension counting. We want to show that for each of my conditions, the space of quadrics where it fails has codimension at least 1 in the space of all quadrics, because then a generic quadric won't satisfy. Or sorry, the pencils where it fails has codimension at least 1 in the space of all pencils. And the way you do dimension counting is you look at all the points where the condition could possibly fail. So for example, the points where DF could intersect the character cycle of K. And you look at each point, what's the codimension of the space of pencils where the condition fails at that point. And then if you subtract from that codimension the dimension of the space of points, that gives you a lower bound for the codimension of the space that fail at any point. And so you just, it's a very by hands argument. You can figure out the codimension, you can verify it's always at least 1. So the last thing to do, we have a formula for the characteristic cycle, and we need to check that this operation of removing the fiber and applying I shriek preserves the polar multiplicities up to a shift by 1. And so we kind of put down on each side, we write down the formula, the definition of the polar multiplicity in terms of an intersection. And we try to compare the two intersections. So the general idea is the easy way to compare them is to make the two generic subbundles that appear in them to make those two bundles related. So we can take a generic subbundle of a cotangent bundle of H and look at its inverse image along DI. And we want to check this is generic enough as a subbundle of cotangent bundle of X. And then we can take a smooth subvariety of H, which we're going to use to calculate the polar multiplicity. And we can embed it into X. It's still a smooth subvariety of X. And we want to check that if the H subvariety is sufficiently generic, then the X subvariety is sufficiently generic. And we'll use the fact also that H is sufficiently generic in X, or otherwise we run into trouble. And so again, the strategy is to be very precise about what I mean by sufficiently generic, work out exactly what condition is needed for the argument, which turns out to be related to the blow up of the cotangent bundle. If we blow up the special fiber and just check it holds in an explicit manner. And once that's set up, once you check, you can use kind of related bundles to calculate the intersection numbers on the two sides. Then relating the two intersection numbers is like chasing diagrams around using the projection point. So the last thing I want to say is I think there's a lot of possible directions you can take using this result. There's many different complexes that show up. For example, in applications of number theory. And if you can check one of them as perverse, calculate the characteristic cycle, and then estimate the polar multiplicity of the characteristic cycle, then you'll get a new bound. And a lot of times, one or more of those steps will be some kind of interesting question. So sometimes they're easy, sometimes I have no idea how to do them. It varies. And maybe the most interesting case is as Hecke eigensheaves, I feel like, because it's connected to a lot of different geometry. The general philosophy is line length of the characteristic cycle should be related to the nilpotent cone of the space of Higgs bundles. And there's interesting intersection theory involving the nilpotent cone that I don't know how to do. Yeah, so that's all I have to say. But to thank the organizers for organizing.
Thank you very much. It was a beautiful talk. And first I will ask if there are any questions from the room. Yes, Takeshi.
So thank you for the interesting lecture. So today you talked on the the dimension at 1 point, stalk at one point. So can you say something on the global thing, like global cohomology, dimension of global cohomology?
Not using this method. I mean, you could try. Well, I guess there's one thing you could do. So, for example, if you have a sheaf on affine space, you could try to express the global cohomology as the stalk of like the Fourier transform at the point 0. And then your sheaf would be perverse, its Fourier transform would be reverse. So if you can calculate the characteristic cycle of its Fourier transform, you could just apply this method directly to study the stalks. The other thing I would try to do, which is not related to this method, is to use the Lefschetz hyperplane theorem to intersect with the generic hyperplane, and you can using iteratively applying the Lefschetz hyperplane theorem, you can relate the global cohomology to the Euler characteristic of the sheaf and the Euler characteristic of its intersections with various hyperplanes. And each of those Euler characteristics can be expressed using the characteristic cycle. So that should be a good approach to global cohomology using the characteristic cycle.
Thank you.
Are there any more questions from the room?
If I'm understanding correctly, your result is a local result, and
yes,
and in your method you use the global quantity. Do you think this can be a more local proof?
I don't know. Maybe I didn't come up with a more local proof. Perhaps somebody else could. I would strongly suspect that there is a more local proof, but I didn't know how to do it.
Okay, maybe
you have a virtual question.
Okay, so the concerning the last question, just when you go back to the characteristic 0 case, of course you can work on complex varieties and sheaves constructible for, let's say, analytic stratification. So the Massey estimate holds for in the complex analytic case also, or not?
I believe it does. Yeah, I believe Massey.
But of course, the proof, the kind of proof that you have uses global, I mean, some global argument in a projective space. So
yes.
So of course, you can then maybe use Artin approximation or something to show that you can essentially reduce the algebraic case. But so the question was whether in characteristic 0, whether the proof. So the proof in characteristic 0 follows the same lines as you said, or it is local?
So I think this step, this is where I use the global. I mean, my proof is mostly local, and here's where I use a global argument. And I think the rest of the argument is pretty similar to what's done in characteristic 0. So in particular, what Massey does is he writes a general map F, and he takes nearby cycles and vanishing cycles, and then he iterates that. So he expresses it in a slightly different way, but it's the same idea. He does iterated nearby cycles, and iteratively applies the vanishing cycles long exact sequence. But he has I don't know exactly how he does this step of calculating the characteristic cycle of the nearby cycles sheaf. I actually found the paper, I didn't have the easiest time in the world of finding the paper because it's written in a different perspective than the way that I think. But he works with complex analytic maps, so he definitely is not using like global Euler characteristic logic. I mean, this formula, it seems like the kind of formula, this nearby cycle formula, there should exist a local proof of, but I found the global proof and it was reasonably simple, so I didn't bother looking very hard for a local proof. I mean, maybe, I don't know, maybe one of you could find one if it's interesting.
Okay, and in the course of the proof, you say that you have a pencil of quadrics and you blow up at you blow up at the indeterminacy locus, which is of course away from the point you're interested in.
Yeah.
And then you have to calculate the characteristic cycle under the blow up to make sure
if you could do this step locally, you wouldn't need to worry about the blow up, because then you could just pass to an affine, like an open set where the map was well defined. So if you could do the previous step locally, then what I would probably do in this step is I'd go to an affine open and just choose a generic polynomial map rather than a pencil of quadrics in the global set.
Okay, but since you need the global thing, so apparently you need to calculate the characteristic cycle of the pullback under the blow-up in order to control in the idea of the argument, there are no other points where the characteristic cycle intersect after blow-up intersects the graph of df.
Yeah.
Okay, I understand roughly the. Okay.
Yeah. So.
Okay. Are there any more questions from the room or from Zoom? No. If no more questions, well, then let's thank the speaker again very much. And as it is the last talk of the conference, I think we should all thank the organizers for their wonderful job. And